Vai pure quando vuoi.
Hello, my name is Giorgio Soli and I am here to introduce a lesson developed within the Microcloud Electronic Alliance by the company Astel. In this lesson we will deal with the handling techniques of critical silicon wafers, and we will use a case study related to an inspection system, which is one of the cases where all the techniques are often used to handle normal and critical wafers. Just to give a brief introduction, we will briefly discuss about what is a wafer and which is the process related to it. A wafer is normally a substrate of semiconductor, but not only semiconductor, which is used to manufacture electronic components. Generally speaking, there is a process in which a crystal of silicon is grown around a semen inside a melted silicon. Silicon is then cut in slices and then prepared for the next phases. The next phases generally are a lot of mechanical tooling over the disk obtained, and then implantation and deposition of different materials, and etching and lithography through basically photographic techniques. With this sum of techniques, electronic components are obtained by obtaining junctions and connections in between them. Of course, this is only a brief description, and many details are missing. But starting from the bare wafer, we will arrive to have a wafer complete of components like this, and components will later on be cut to be encased inside the final components, which will be used in practice for any electronic devices. Then, dealing about wafers, we have different type of materials. Here we can see silicon carbide, lithium niobate, sapphire, but we can also have ceramic, we can also have germanium, and a lot of different substrates with different features, weights, dimensions, and so on. Dimensions are spanning from 2 inches to the so-called 12 inches, but in reality is 300 millimeters, and now we are going toward the 400 and 600 millimeters in diameter, while thickness is from less than 40 microns to even more than 2 millimeters. So here we have a brief example in this video where a wafer 60 micron thick is handled by a system, and looking at how this wafer is moved, and especially what happens when wafer is moved through the different positions, like here, you can see that the wafer is really floppy. It is important to keep in mind that the wafer is basically something like a piece of glass, crystal glass, but very thin, very critical, and often very, very expensive. Here we have some different example of what we can do with wafers, and which are the new frontiers of the wafer manufacturing. At the beginning, wafers were used only to manufacture electronic components, basically diodes, transistors, and integrated circuits, integrating diodes, transistors, and passive components inside them. Now the new frontiers are manufacturing something which is called MEMS, which is microelectronics mechanical systems, which includes not only an electronic part, but also mechanical parts, like, for example, moving mirrors or membranes to obtain microphones or membranes to obtain sensors of any kind. MEMS requires to have perforated wafers, a composition of different wafers stacked together, and so on. Another frontier is the ultra-thin wafers. Again, at the beginning of the technology, wafers were used more or less at the full thickness. Later on, for example, to include a chip inside a credit card, it was needed to go down in thickness down to less than 100 microns. And manufacturing thin wafers began to be one important thing in wafer manufacturing. Now, just to introduce what are we dealing with, we have different mechanical characteristics for the wafers. Wafers are basically a disk of material, but a disk which is normally not flat. Or better, it is flat when the wafer is thick enough and stable enough. Normally, when a wafer is a bare wafer, I mean a wafer cut from the crystal, it is flat. During the process, due to the phase of the process where we are going to add material, to add tooling over it, it will accumulate tensions inside the structure. And those tensions are in some way deforming the wafer. If the wafer is thick enough, this is not so visible. But when we start to reduce the thickness, wafer will move and the surface will change. We have basically two types of modification of the surface. The first is called bow. Normally, it is due to the weight of the wafer itself. If we take a wafer and we support it on a side, its own weight tends to change the surface, and normally it's bent toward the gravity. But maybe also that a process will add a different material which will create a tensile modification, and then bow can be negative. But 99% of the bow is positive. The other case is the so-called warpage. In this case, we have a process or a sum of processes which acts in an unpredictable way. This will make the wafer to be really similar to a potato chip. And we can see on this small video how a wafer can be warped. This is really a not normal case, but there are cases which are similar enough to this. By the way, this type of wafer in the video is almost impossible to handle, except if we use some special techniques like the Bernoulli system, which we'll discuss later on. Other features which can impact on handling, and especially with MEMS, are perforated wafers. To make a MEMS, normally we have a substrate which is dedicated to the component, and a second substrate which can be dedicated to the mechanical part. That's just an example. There are a lot of different possibilities. But anyway, a MEMS normally is perforated. Maybe the holes are passing through the whole surface or stops on the first surface, but in any case, this is an additional complication to the handling. If a wafer is completely perforated, it's difficult to handle it, and we will see how and why it will be difficult. So, now we are just at the core of our presentation. Now, the real topic is critical wafers handling. It is not so difficult to handle normal wafers. Handling critical wafers is very, very difficult. Okay, now we see just how wafers are moved along the process into a factory. Normally, a wafer is moved through carriers or cassettes during the different phases of production. And just to give a small information, the production of a single wafer can take a total amount of 3 months or more than 3 months, depending on the phases which are applied to the wafer, but no less. And the wafer is contained in such type of cassettes which are more or less standard and which are compatible with all the tools used into the process. We see here a normal cassette, a transportation cassette, a cassette for wafers on frames which are used at the end of the process, and some transportation cassettes which are used to move normally a wafer from one factory to another location. Then let's see an example of how wafer handling was and in many cases is done. Okay, here we have a lady, 2 cassettes, and the task is moving wafers from one cassette to the other. The lady is using some a small tool, a kind of gripper, working on the edge of the wafer and keeping as possible firm the hands, is moving wafer from one cassette to the other. You can see that anyway this is not really safe, because if she makes an error in taking the wafer can slip down and break, for example, or she can make a mistake in putting in the new carrier. And anyway, this setup is not clean enough. We will see later on that cleanliness is one of the most important features. In this small video, we can see a transfer of wafers between one carrier to the other. What we can note from the previous video and this is that the size, I mean the diameter of the wafers, is not so high, and the thickness is relatively high. Okay, now the problem is we must do it better. How can we handle the wafer better than what we have seen before? Because remember, we are not dealing with normal wafers, but with wafers which can be thin, warped, very big, or on the other hand, thick, heavy, and anyway critical and fragile. And remember, very expensive. Okay, what we have to do and we don't have to do in handling wafers. First, we have not to break wafers. That's extremely important because a broken wafer is a scrap. And each single component has its own value. We can have up to 1,000 of components on a wafer, and so breaking a wafer, for example, at the end of a process, can result in a real big damage in terms of billing, but not only, also in terms of organization of the job. So this is one of the worst cases. But also we can make scratches or contaminations. Scratches can be a problem at the end of the process, but also at the beginning, and the contamination as well can be a problem. Contamination can be metal contamination, which will impact on the first phases of the process, for example, the implantation and so on. And in this case, we are going to put alien material inside a doping, in the so-called front end. The other type of contamination can be particle contamination, which can be very critical when we are going to create the geometries on wafers. It's important to remember that the geometry of wafer can be less than 1 micron in thickness and 5-7 microns in thickness. If we think that a single piece of dust can be more than 3 microns, and even more, of course, we can understand how a particle can destroy one component. And that's the reason why wafers are always manufactured in clean environments. Okay, now, this is one of the most critical part handling wafers. The so-called end effector, which is normally called also arm, is the part in direct contact with wafer. It's not the only part. Generally speaking, there are 2 parts in contact with wafers, end effectors and chucks. End effectors are the parts which are going to take wafers from the carriers and move along the whole process inside the tool. End effectors can be done of different materials, with different geometries and with different techniques. Normally, there are used 3 types of materials. The first is metal, the second is ceramic, and the other is composite materials like carbon fiber. All those materials have advantages and drawbacks. In any case, for example, metal can contaminate and easily scratch a wafer. And if there is a mechanical problem, metal can bend. On the other hand, ceramic is much more stable, but is easy to break. carbon fiber is flexible, is very stiff, but is not able to go to high temperature. Normally, we can use mechanical gripping or vacuum. And vacuum is the most common solution used to handle wafers, not only for end effectors, but also for chucks. When we have to keep a wafer in position, since its surface is perfectly flat, we can apply a vacuum under it, and the vacuum will keep it perfectly in position. Also this, in case of critical wafers, must be done according to some guidelines which we will see later on into the case study. One interesting way of handling wafers is the so-called Bernoulli effect. It's basically a vacuum system to move wafers, where the vacuum is obtained by a fast flow of air. Creating a stream of air will create a vacuum around it. So we are able to attract in some way the wafer against the Bernoulli unit. But there is a point where the air flowing out from the Bernoulli unit and the vacuum against the wafer surface has a balance. In this point, the wafer will stop and the wafer will not touch the surface of the Bernoulli unit. In this way, it is possible to handle wafers from the active layer, and we did not tell that normally wafer has an active surface, which is normally the upper surface, and a surface which is normally used just for handling it, which is the bottom. There are cases in which components are on both sides, but okay, we are not dealing about with this. In any case, with Bernoulli, we will not touch the active layer in any way. We will see later on when we can use this or where it's used. Okay. Now we are starting with our case study. Our case study is a wafer inspection system. Wafer inspection system is an optical inspection system based on a microscope and is intended to inspect the wafer more or less along all the phases of its process. That's why an inspection system is normally a critical handling system, because it's used in the first phase of the process, where wafers are not so critical in terms of mechanical handling, but are very sensitive to any contamination, and is used also at the end of the process, when wafers can be very critical in terms of mechanical handling, even if not so critical in terms of contaminations, but are much more high in value than a wafer at the beginning of the process. Then, which type of wafer we have to inspect? Almost all. From the bare wafer to see if on the wafer there are defects of any kind on the surface, to wafers at the first stages of the implantation during lithography, just for example to judge if the photoresist applied is applied in a correct way, and then moving toward the end of the process we can have thin wafers with high bow, high warpage. We can also have perforated wafers, MEMS, and so on. So an inspection system must be able to handle such a kind of wafer, which means all. Okay, which means a full manual optical inspection. Normally, an optical inspection is composed of two basic parts. One is the normal microscope inspection, and the other is the so-called macro inspection. Macro inspection is just looking at a wafer on a collimated and structured light just with the eyes. This is used to highlight macro defects like scratches, cracks, fingerprints, dust, and so on. This is done not only on the front side of the wafer, but also on the back side of the wafer. And in moving wafers is important to keep them safe. And the second part, as we told, is the microscope, which is intended to inspect the micro structures. Of course, this can also be done completely manually, like we have seen previously in the video of moving manually wafers from cassette to cassette. We can take a wafer with a vacuum wand or a mechanical gripper, use a light to inspect it front and back, place it on a microscope, remove from the microscope and put it into the carrier. This can be relatively easy if the wafer is full thickness and normal in structure, can be almost impossible if the wafer is special. So to do this kind of task, we have different levels. The first level is this, auto-loading and manual inspection. In this case, we have a wafer loader, which is simply an equipment which will take the wafer from a carrier, put it on the chuck of a microscope, and allow the operator to look at the wafer under the microscope. We can see in this small video how a system like this works. The carrier is placed on a platform, then the system is started. There are some operations which we will describe later about the specific case study, but anyway, the wafer is extracted from the carrier, placed on the microscope, and then inspected. Again, wafer is taken and driven back to the carrier. We can see here a detail of how it's moved. In this case, we have an end effector made by carbon fiber, and also we are able to rotate the wafer under the microscope because we need to have the wafer aligned to our geometries to inspect it. In this case, to keep safety, wafer is rotated back to the original position to avoid hitting the edges of the carrier. Now we can move forward and go directly to the description of our case. Okay, in this case, we will analyze a more complex system. Basically, it is handling wafers like we have seen before, but we add macro front inspection, macro back inspection, and micro inspection. This implies a lot of additional complications. What we have seen before is a tool which is not going to make any centering of the wafer, and the alignment is done manually. In the case of an automatic system which needs to make macro front and back and then micro inspection, it is needed to keep perfectly the center of the wafer and its perfect alignment. And then at the end of the process, we have something like an assisted optical inspection where we can work on defect review. We will describe later what this means, because this is an important part, not related especially to the handling, but to the whole process, the traceability of the results we have, which are anyway a part of the safety in wafer production. Okay, here we have a video where we have an example of the different phases we will describe later. We have the carrier, which is moved into the platform. The wafer is centered and placed on a chuck for macro front inspection. Macro front inspection is done by moving the wafer under a structured light. Then we are going to take the wafer with a Bernoulli unit. With the Bernoulli unit, we lift it under a second collimated light, and then we are going to the microscope inspection. To do this, we need, again, centering and aligning the wafer. Then we go to the microscope, and we need to identify which wafer we are working on. What we did not tell before is that each wafer is identified by its own code, which is used to trace the wafer production along all the phases. Here we are looking at what happens next. Under the microscope, we are able to address each single component and to identify the defects present in the component itself, take trace of them, and so obtain a complete documentation. Again, this is not really related to how critical is a wafer. It's simply an example of what it is needed to do to obtain a good production process. Okay, we can go again. Yeah, we are just explaining how a system like this, like the drive-in inspection is working with wafer alignment and so on, but we can go further because this is something which is not really related to handling. Here we can see briefly and explain briefly what an operator is doing on a wafer. He is able to inspect, as we told, each single die, looking at on the microscope or on a computer screen, take pictures, take measures, make a documentation of the defects, and so on. Okay. Now we are going to discuss the techniques we need to use to obtain what we have seen before. The techniques are intended to make the tool able to handle any type of wafers, and the aim is to avoid to the operator to take critical decisions, which can result in human errors and then in wafer damage. Okay, let's start from the beginning. This is a carrier seen from the front where some wafers are present. Wafers can be of any kind with bow, warpage, and so on, and must be identified. Identified means we need to know where the wafer is to handle it correctly. At the beginning of the technology, this was done simply by supposing that the carrier was full. So a vacuum pad was put inside the carrier trying to take the wafer. If the wafer was not taken or detected, it was assumed that the wafer was not present, and then the system was passing to the next wafer. Of course, if the wafer was present, the phase of the process was missing, and the wafer was a scrap. This was the early technology. The second step was identifying which wafers were present into the carrier. This was done through a laser system, but it was just looking if into a slot a wafer was present. Then the handling was made supposing where the wafer had to be taken and so on. The last and more actual technique is position measurement. In this case, the wafer is through a laser beam measured in 8 and position, and it's possible to judge not only the wafer position, but its relative position related to the other wafers, how is near or far from the wafers, so we are able to judge if it's safe to go to take this wafer or not, which is the apparent thickness of the wafer. Because if the wafer is bent or warped, seen with laser beam, its thickness is more or less high, and definitely we have a possibility to go to handle wafers in a really safe mode. Then, this is a typical case which can be detected by a laser mapping. The second wafer is misplaced. It's placed through 2 different slots. This kind of defect in placement is called cross slot and is very dangerous, and normally is done when the wafer is handled manually, but not only. If we are trying to handle automatically, this wafer is very easy to break it. Another safety issue is the protrusion of the wafer from the carrier. If the wafer is out from the carrier too much, it can hit parts of the machine or can be broken by other movements, and so in this case it's very simple. A reflection sensor can detect if one or more wafers are protruding from the carrier. And then let's go to the real handling. Once we have exactly identified where a wafer is, if we can handle the wafer because we have the safety conditions, if the wafer is not too out from the carrier, we have to go to take it. And the factors, as we told before, are the tools used to take the wafer from a carrier and move it along all the phases inside the tool. Different wafers, in case of critical wafers, of course, requires different kind of techniques. In this case, we have two examples. In both cases, we are showing carbon fiber and effectors. On the first end effector on the left, we can see we have a set of micro holes which are working on the wafer surface to create a sort of vacuum area. In the second case, we have an adhesive pad where the vacuum is created by the slot inside the pad. In both cases, vacuum is used to handle wafer. In other cases, for example in MEMS, where we have perforated wafers, we can use again the micro holes technique, but we need to go to take the wafer in the area just close to its edge. Each wafer has an edge exclusion area where components are not present, and we can use this area to move critical wafers without going into the perforated area. And so we can also handle wafers where the application of vacuum can be potentially damaging the wafer. Okay? Now, once we have taken the wafer, we must be sure that the wafer is in the position where we want to have it. This means being able to know where the center of the wafer is in each moment. This operation is called centering. At the beginning of the technology, mechanical systems were used for centering. In this case, we can see two sectors moving on the edge of the wafer to move it to the center position. This is not so nice because we can damage the wafer and in any case not precise. Other systems could include in the past some cones taking the wafers, leaving the wafer fall down into the cones, or pins, or other type of pushing mechanisms. Anyway, the results were not precise enough and not safe enough for critical wafers. Okay, now we are going to the next step, which is measuring with a no contact system the position of the wafer and correcting it by an algorithm and a motorized system. In this case, we measure typically the position of the edge of the wafer. We see how it's displaced from its ideal position, and then we can correct it. In the case we are describing, we use a linear motion to correct the X position and a polar rotation to correct the Y position error. We'll see now a very fast example of centering. We are just going inside the two sensors. Okay, let's repeat. We see here we are reading a chord of the wafer, and then we are able to place it perfectly centered here. Okay, now we have a next step. Wafer must be known in its position in space, which means that we must know its center. But also, devices on the wafer must be aligned, because in each step we need to align the wafer to the previous step and prepare it for the next step. This is called wafer alignment. A wafer is identified for alignment by different type of mechanical markers. The smaller sizes as the so-called flat, which is a flat side on the round. On the round shape, we can see here, we have a flat side. It's very simple to identify a flat side, because if the wafer is centered, it's simply a reflection sensor which is able to detect the reflection of the flat. So in this case, we have seen centering and flat identifying. And this is very simple. With the bigger wafers, we have the so-called notch. Notch is really a notch on the edge of the wafer. Notch is very small. It's something like 1.5 millimeters deep and 3 millimeters wide. And we must identify it precisely normally during a wafer rotation. Identifying a notch is, of course, affected of how precise is our centering. And it's normally very difficult to catch a notch by an on-off sensor. Even if we place a perfectly aligned laser sensor, maybe if the notch is not perfectly aligned, we can have a big enough error not to detect its alignment. So, the technique we are describing here is the use of an area sensor and a large beam emitter. The wafer is rotated over the receiver, and then we can obtain a projection of its edge. In this case, we can see here, we were just detecting a flat and not a notch, but it's the same. The notch is a small peak, a flat is a bigger peak, and here we have a reconstruction made by software of the wafer edge. In this case, we had two different flats. In any case, with this system, it's very easy to identify the precise position of the notch and proceed to a perfect alignment. To do this, we need anyway to place the wafer on a vacuum chuck. Vacuum chuck is another part of wafer handling. It is important, depending on the phase where the chuck is used, its shape, its dimension, and the type of material, the treatment, and so on. In this case, this is a small chuck which is used for macro inspection. But for example, in case of microscope inspection, we need to have, if possible, a larger chuck to avoid the bending of the wafer and allow to have a more stable focus position on the microscope. Vacuum chuck must be done to avoid to stress wafers. Normally a chuck is done by vacuum technique. There are different techniques. This is a micro holes system. They are also something like a porous ceramic, and in some cases also electrostatic chucks are used. In any case, a chuck must be flat, keeping firmly wafers and give no contamination. So the material and the treatment are very important. The next phase in this machine is back inspection. While on the previous chuck we could do macro inspection and alignment, on the Bernoulli unit we are going to do back inspection, as we have seen in the video before. Bernoulli unit is driven over the wafer at a given distance, and the flow of air is activated. There are some needs of precision in the distance, and especially in how the flow of air is applied to the Bernoulli unit. It is important to have a modulated air flow to avoid that the wafer is detached from the chuck in an abrupt way, and in this way can touch some parts of the Bernoulli unit or hit the flat of the Bernoulli unit itself. And also for release, it's important that the release is soft to avoid that hitting the chuck wafer can be damaged. Okay. In handling, there are also other not so evident factors which are very, very important. A system like the one we have seen needs a precise control of motion, IOs, sensors, and emergency conditions. For this, it has been developed a board including a precise motor control with different types of possible programming for each motor, where we can program, for example, speeds, acceleration, deceleration, and so on, just to make the movement as smooth as possible. We can control IOs in an integrated way, mixed together with the motion, without having to address different boards. And we can also, in this case, control the sensors for vacuum, pressure, and so on. Also, and this is an added value, it's not a safety issue, but a tool anyway must be easy to repair and maintain. Having a system with a lot of boards makes the system difficult to repair. Having a system with a single or two single boards is easy to maintain and then really cost effective in terms of cost of ownership. Of course, it's also important the software we are implementing on the tool. About safety, and with critical wafer, but also in general with wafers, safety is the main issue. we need to have a software which must be simple to use. Simple to use means less mistakes from the operator, and this reduces dramatically the possibility to damage wafers. Second, we must be able to handle in the correct way all the information coming from the sensors, from the IOs, from the motors, and so on. And this is implied into the software. Again, we must be able to program each different type of wafers in terms of its own handling. And so it implies the use of dedicated recipes. This is obtained by a software which interface must be as intuitive as possible. Then, last but not least, the human factor. It seems that all the techniques we have described are enough, but it's important that the techniques are applied in a coordinated teamwork which has a good documentation, good procedures, and a repeatable process where people work in a coordinated way to obtain the final goal of a perfect tool working for years without damaging wafers. Thank you for your time. This was the presentation from Astel, and by the way, I am the left on the right side.